The current numbers are Wednesday night 31, Wednesday afternoon 23, Thursday afternoon 16, and Friday 28. Merging a couple of people towards Thursday would be good. The current count is 98. We lost another one. Let me remind you that for homework 1, there is a table in which so this is a searchable word. There's a VOL parameter, which is the voltage at the pin when the output is supposed to be low, that is to say driven by 0 volts. And another line of a table which gives the V output when it's supposed to be high. And you will find using that data that there is a different Thevenin equivalent for high and low, Thevenin equivalent resistance for high and low voltage value. One other note, I slightly modified Lab 1. I added another example code that shows how to use EEPROM. Since I assigned that you should do that, it seems reasonable to think that you should get some idea of how to actually implement EEPROM. It's really easy. Any questions about the homework? Any questions about Lab 1? Pavel.
So we just mentioned that people that are not in groups yet, we just bring their homework today.
Right. The policy page specifies that homework and all assignments are done as a team, as a group, but of course some people don't know who their group is yet. And if you don't have a partner, then bring your homework in and we'll sort of merge homeworks in some nonlinear fashion for groups after when we figure out where the groups are. Anybody who doesn't have a partner will get a partner in lab. I'll be in lab this afternoon. I'll be in lab tonight. Every week I'll be in the afternoon labs, but the night lab is only tonight. I can't take 17-hour days anymore. You know, it's too hard on my body. So it's another. But tonight I'll be there because I like for the first lab to kind of do some level setting and show people where the hardware is and what they should put away and what they should leave at the station and where to put projects when you're not in lab and yada yada. There is still one person. I sent out a broadcast email today to give a link for the EEPROM code, and one person is still forwarding mail to Yahoo, which is bouncing it. So if you forward your mail to Yahoo, you're probably not getting the mail. I can't figure out how to read the darn header to figure out what the net ID is. It seems to be buried someplace and I can't find it. So if anybody knows how to read a mail header better than I'll take the help. Otherwise, turn off your Yahoo account. Who uses Yahoo anyway? Unclean. So I started out talking about LCD demo program last time, and you may or may not have noticed it, but I confused two different versions. The version that's on the web page, on the lab page, is the new, improved, updated version, and the one I started lecturing about was the old, unimproved, sleazy version that used delays. And the new, improved version does not have a delay statement in it. And so it is in good form, not poor form.
When did you update it?
When I updated it a year ago. The update failed to occur here. It occurred on the web page, but not in my brain. These things happen. All right, so I think the last line I put on the board last time for the demo, which is, it turns out the same for both the old version and the new version, was include LCD underscore live.h, right? Okay. So, first thing we're going to do is define some constants that are going to be used with the LCD. So we're going to define a constant int 8 underscore t. So this is a 8-bit integer, a car. This is equivalent to a car. And we're going to use the keyword progmem, which says to take the string line 1 \0 and store it into flash memory. It's going to store it into program memory. Remember that there are 3 different memory architectures on the chip. There is flash, which stores program, and you can optionally put read-only data there. There is RAM, which of course is read-write. And there's EEPROM, which is also a flash memory, but it is not for data storage. Sorry, it's not for program storage. In fact, no program can be executed from RAM or EEPROM. EEPROM is designed for putting a small number of constants in that you need over and over again in your program and which you cannot afford to load every time. And an example would be a volume control setting that a user can manipulate, and you want to store the volume control setting so the next time the system is turned on, it comes on at the same volume. So a few numbers, 1,000 characters or so, you can put in EEPROM. EEPROM must not be written every time through main. EEPROM can be written about 100,000 times. If you put a write to EEPROM in main and gets executed 1,000,000 times a second, that memory won't be there anymore. And so EEPROM has to be written sparingly. You can read it all you want, but you can only write it 100,000 times, and that typically means that you would write it when a human does something, like push a button. You would do it when the human asks to shut down the system, or when a key is pressed, but not just because another millisecond ticked by. Any questions on that?
You say we can't use program in the RAM or EEPROM, but can you write data to the flash?
You can write data to flash at program time, but not at runtime. So when you download a program from the PC to the microcontroller, the downloaded memory image can include data, but then your running program on the microcontroller cannot modify that data. It can read it. Reading's about half the speed. It reads in 2 cycles rather than 1 cycle. RAM reads in 1 cycle. Flash memory reads in 2. EEPROM reads in 2 and writes in about 100 cycles. It's rather slow to write, fast to read. Any other questions?
You say it writes in about 100 cycles. Is that like a serial write, so it blocks with the program, or does it write in parallel?
It blocks the program because it's doing a bunch of manipulations. You don't want to do this very often. You don't want to write the EEPROM very often, both because it's slow and because you'll just use it up. 1 byte at a time, write zeros. By default, if you do nothing to EEPROM, it reads back FF, all ones. So I'm here asking that the string line 1 \0 be stored in progmem, and the double quotes mean convert every character to its ASCII equivalent and store that ASCII equivalent integer into 1 byte. So now we're going to define another constant. Number equals \0 quote. Because the format we're going to ask for is on the LCD. This is supposed to be a blown up version of the LCD screen. Is going to be the string number equals, and then there's going to be a 4-digit count that is appended on this line. And down here, we're going to have the string line 1, and then a cheesy animation over here, which is going to be the letter small o, lowercase o, moving back and forth 8 characters, back and forth. Because I'm an idiot? Because I left something out? I left something out. Oh dear. I hate it when I do that. Thank you. We better give this a name. LCD line bracket bracket progmem equals line, etc., and LCD number square brackets progmem equals number, and etc. The square brackets is a notation for C to look at how many characters are in the actual string and to reserve a chunk of memory, to dimension a chunk of memory, reserve a chunk of memory of the appropriate size to hold it. Using the square brackets here says, I'm going to need a string, but I don't really know how big it is yet. As opposed to the next line, where we're going to specify that we want now an int 8 underscore t of LCD buffer, and we want this to be precisely 17 characters. We're going to choose 17 characters because the width of the LCD display is 16 characters, and so the widest string we can expect to print on it is 16 characters. We need the 17th character to hold the \0. This is going to be a general purpose print buffer.
Why are you using an 18 instead of cars?
No reason.
And what is the progmem?
What is progmem? It means use flash. Store it in flash, not in RAM. For this little program, you could store it in RAM, not a problem. However, if you store a string in RAM, you have to change the LCD functions that are used to draw the string because flash and RAM have different pointer structures. And so if you expect to output constant strings using copy string to LCD, it has to be from flash.
But the buffer is not in flash.
Buffer is not in flash. The buffer is in RAM.
Would we copy the buffer to flash first?
No, you can't copy to flash. Flash is read-only. There is a different call. There's a different function we're going to use to write RAM strings. And we need a int, which we probably should write as a uint 16t, uint 16t to be device independent, count, and uint 8t, animation position, anipos, A-N-I-P-O-S, and a direction, whether it's going right or left, whether the cheesy animation is moving to the right or left. And we're going to define the T1, the time for the first task to re-execute, of 200 milliseconds. And we'll find out that this is going to be the update time for the LCD, so we would expect to get about 5 frames per second off of the LCD. We also need a volatile int 8 time 1. So first thing we're going to do is init the LCD. And by the way, init LCD is synchronous. It will not exit until the LCD comes back saying that it is successfully initialized. Therefore, if you say, I'm just going to test the code first before I hook anything up, and you have an init LCD in the code, it'll halt there forever because the LCD never acts. It never acknowledges. And so if you code up an LCD init, you must have a properly connected LCD or nothing will ever happen again in your program. So we're going to code up a let's make that void. And we're going to call a low-level function LCD init. This is a horror of assembly code and C. If you want to have your brain twisted, take a look at this baby. There's a whole bunch of weird state code that has to go in there to put the LCD in a known state. You turn on the LCD, it has a state machine running in it. You have to put that state machine in a known state, and you have to go through a whole bunch of fiddling to get it into the correct state. Then we're going to turn LCD cursor off. The cursor is either a blinking cursor, a block cursor, it's an insertion cursor. Since humans are not going to be writing to this device, you're not going to be typing while looking at the LCD, although you could. There's no reason to have an insertion cursor. It just is distracting to have it blinking, so turning it off. And we're going to do an LCD CLR, LCD clear, and end. Let me remind you, if you execute LCD init and you get weird characters, or it doesn't seem to clear, or it starts scrolling garbage, it's because you have the clock frequency set wrong on the CPU. Now there's going to be a timer timer 0 interrupt just like there was in the last example, so I'm not going to write it out again. It's going to increment time 1 once per millisecond so that we can tick milliseconds off. And main is going to dispatch task 1 every 200 milliseconds. So I'm not going to write out main in the interrupt service routine because they're identical to what I wrote last time, last example. So we're going to go directly to writing out task 1, which does all of the work. Almost all the work. No, maybe I won't do task 1 first. Maybe I'll do main first. What a concept. So the first thing we're going to do then is we're going to init LCD. Then we have to set up the timer 0. Time mask 0 equals 2 OCR 0A equals 249. TCCR 0A equals 0 binary 10. And TCCR 0B equals 3. That's setting up the timer exactly the way it was before, but using a little less nice notation.
Where do we link the actual physical port to the LCD? Where are we telling?
Oh, where do you link the actual physical port to the logical code? It's in lcdlib.h, I think. It's in the header file, and there'll be a port definition there. It's either that or it's in libc. The library you have to associate with it, but I'm pretty sure it's in the header file. I think it defaults to port C.
Okay, so there's a default port.
There is a default port.
Okay. So if you wanted to change it, you'd have to go in the header file.
And manipulate the header file yourself. That's correct. So once we've done this, then we're going to do a copy. Love these verbose function calls. Copy string to LCD. LCD underscore line. So this is one of the strings stored in program memory. And we're going to put it at position 8 on line 1. So this is a location of a string in flash only, not in RAM. This won't work for RAM. It'll work for flash. And it's going to be at position 8 horizontally, position 1 vertically. And everything's 0 based. Then we're going to do a copy string to LCD, LCD number, I think I made it. And we're going to put that in at the left. We're going to left justify it to position 0, line 0. Then we're going to initialize some state variables. We're going to set the count equal to 0. We're going to set, and then we're going to, animation position. ANI pose equals 0. And then we're going to do an LCD go to XY. I didn't think up this capitalization scheme. LCD go to XY and a position one. Line 1 at the animation position, and then do an LCD sand car, single tick, little o, single tick, and then of course we're going to have to turn on the interrupts with an SEI semicolon. Now, there's a very annoying C notation here. That help slightly? See somebody peering over the desk. Can you see? Sort of? Can't pull that off, put it on the table. So, there's an annoying C notation here. Single quotes is a string. Double quotes, no, wait a minute, that's MATLAB. That's why it's annoying. Double quotes are a string. Single quotes are not a string. They're a character. This does not do a string conversion. It simply stores the character value in of lowercase o. So who can pull that out of memory? What's the value of lowercase o? 96 plus 13, 14, plus 18, or plus 15 or something. So you have to be careful. This does not append a \0. It does not do any processing. It merely converts one character to an integer value.
If you put OO in there, what would
Oh, it would blow up.
So if you use double quotes, it doesn't automatically append the null character?
It does usually append a null character, yes.
Not in the definition?
Not in the definitions necessarily. And then there's going to be a while loop. There's going to be the usual while loop that goes on forever. Dispatching task 1, now 5 times a second. So question? All right. So now we're going to, this is where everything interesting is going to happen, because we're going to take the count variable, which is going to be incremented in this task, and we're going to format it as a string and then put it out onto the LCD. So the first thing we're going to do is a sprint f, sprint f. This means instead of printing to a file unit, we're going to print to a string destination. So C is going to do an internal conversion from integer format to string format for you. I've had many students write their own integer to string converter because for some reason they didn't like sprintf. It's a lot of work. Don't do it. The string destination is going to be LCD buffer, which we've already defined. We're going to tell it how to do the conversion. We're going to say do a % minus I. And if I remember correctly, % minus I means convert to integer, string, and minus means don't leave any spaces to the left. In other words, left justify, don't right justify. that's a straight up C thing. And then we're going to say count plus plus. So this statement does two things. It does the increment on count every time through the task, and it converts the value of count to a string and puts it in LCD buffer. Next thing we're going to do is an LCD go to XY, position 7, line 0, and then do an LCD string. LCD string being the equivalent of copy string to LCD, but in this case it's for going from RAM string to LCD. So we copy the LCD buffer, and it's a really good idea to put in the string length it may be actually required, string length LCD buffer, so that you don't copy more characters than there are LCD positions. Questions? So now we're going to do the animation stuff, the cheesy animation. LCD go to XY, animation position, line 1. And then we're going to do an LCD send car. We have to do an erase because we're going to erase the old position and write new position. The way we do an erase here is that we write a blank. So you can put a blank character between two quotes and it puts out a space. It emits a space. Space is a perfectly valid character.
When you're writing the LCD string to the buffer, but you go to position 7 first, but the buffer is like 16. Is there a reason why the buffer is the length of the whole LCD display? You can only really write to like 8 characters.
There's no reason. It was just I didn't have to think so much if I made it as long as the longest string I could possibly put on there.
Okay.
You know, whenever I can minimize thinking, it sort of keeps the error rate down. By the way, you don't have to call me professor. I am perfectly happy for all of you to call me Bruce. It is going to be a long semester. We're going to spend hundreds of sweaty hours in the lab. I do not depend upon the title for authority. Call me anything you like. One year I did that. And a graduate student in the class said, "Okay, butthead." And so this was a fairly small class in this case. I said, "Okay, you have to call me captain." And for the rest, I almost hate to tell this story because, and I still am called captain by everybody that was in that class. Oh my God, that was 7 years ago. Don't call me captain. LCD send. Okay, so we erased. So now we're going to do the animation dynamics. If the animation position is greater than or equal to 7, then set the direction to -1. If the animation position is less than or equal to 0, set the direction to +1. Update the animation position. update the animation position. Do an LCD go to XY animation position 1 and write the LCD send car small o. And that completes the animation step, the frame step. And then we're going to end the task. So this thing will sit there, if you have it all connected up correctly, it'll sit there and run that ball back and forth and count. There's a couple errors. Let's say that you turn on the power on the LCD and you see nothing on the screen. There's two common reasons for that. One is you hooked up the power wrong. So it's a really good idea to make sure ground is on pin 1 and VCC is on pin 2 and not vice versa, because you can cook these. They're fairly hard to cook, but you can cook them if you leave them hooked up backwards for long enough. The second reason is that you'll notice there's a potentiometer called contrast control hooked to pin 3. If you have the contrast set to 0, you will see nothing. And that sounds awfully trivial, but I'll tell you, I see lots of people hold up their hand and say, I don't see anything on the screen. So did you turn the trim pot? Oh, is that what that's for? So if you don't see something, we have a toolbox. It has screwdrivers. You can turn the trim pot. You don't have to use your teeth or your fingernail or the tip of your mechanical pencil. See if something appears when you turn the trim pot. Then hold up your hand if you don't see anything. If you see a line of black boxes, it means that the power is connected correctly, the contrast is correct, but the initialization code has not run for some reason. It may have not run because the connections to the LCD are wrong. It may not have run because the code is wrong. And probably for the really intransigent cases, the cases you just can't figure out, the TAs will have a reference LCD that you can plug in and see if it works on your system. Every now and then, you'll get a board on which port C has been blown by last year's final project. It's remarkably easy to do. So, I would say that a reasonable goal for this week, by the end of lab, you don't have to be done by the end of lab, but I would say a reasonable goal is have the LCD hooked up and running and be able to make a tone, a controllable tone, out of the little speaker. So when you press a button, you get a beep. I'd say that's a reasonably good start. Some of you will get further, some of you will finish. If you finish today, or this week, you have to come to the next lab anyway, and we'll talk about final projects. Never too early. So let's talk about EEPROM a little bit. Or should we talk about state machines? Yes, what? Yes.
So we need the debounce code?
Yeah, that's what I was going to say. Maybe I ought to talk about debounce code a little bit. And the debounce code here is, you don't have to really do a complete debounce state machine, but I'm going to talk about it anyway. Debounce state machine needs to run as a task about every 30 milliseconds. You need to check a button if you're debouncing it. Maybe a little faster. And let me step back before I start in on that and say that, let me explain the terminology I'm going to use for state machines. So I'm going to define a state, or I'm going to represent a state as a circle. There's going to be some name above the line. There's going to be some test below the line. There'll be arcs leaving the line. which have above the line the result of the test, and below the line will be the action which has to occur on the state transition. So you do tests, you test some variable in the state, you do some action when you leave the state. Of course, you may have this also, it may not actually leave. Debouncing will become much more important in lab 2 and 3 when you have a full keypad you have to debounce, and if you on your cell phone you expect that if you hit the 1 button or the 607 you're going to get 607 and not 6660077. You have to debounce because the CPU and the keypad are so much faster than you that even if you twitch your finger on the keyboard you'll get double hits unless you detect a release before another hit. So you must detect a release, finger up, before you're allowed to get another hit. Since the button bounces, it requires 4 states to do this. You have to test twice to make sure you got a hit, and twice to make sure you've got a release. So a single button debouncer might look like this, where we have some release state, and presumably we're going to enter this from reset, assuming that the user is not deranged enough to be holding down buttons when pressing reset. You could really assume nothing, of course, of a user, which in this case is yourself. The release button, and so there's going to be a test here for 1 button, and we're just going to call it pushed. And if the answer is no, we're going to go back, and on every single transition in the state transition matrix, in the state transition diagram, is going to have a action of check button. The answer is yes. Then the button may be bouncing. Because it's a dynamic system, you push the button in, it goes boing, and finally settles. It may be bouncing. You have to wait 30 milliseconds and check it again to see if it's actually still down. The answer is yes. Then we'll go to a state called maybe. We ask, is it pushed? If the answer is no, we go back here and try again. If the answer is yes, then at this point we know that there is actually a valid button push, and so that it's going to be you're going to set a flag or do a button action, depending on whether you're writing it as an independent task or inline code. You're going to do some button action, and then you're going to fall into a state which is still pressed. And again, we're going to find out, is it pushed? And if the answer is yes, we're going to go back to this state. If the answer is, we'll call this maybe released, and the answer is no, then we'll check the button again, find out, is it still pushed? And if the answer is yes, it means it's still bouncing, and we have to go back to the push state. And if it's no, then we can go back to the release state.
Do you have to do that 4th state, or can you just have it go back to maybe because the results will be coming out?
Wait a minute. Instead of
going to the 4th state, could you just go back to maybe pushed?
Oh, can you?
Does that be maybe released?
That says maybe released.
Yeah, but it could be either. I mean, that state looks the same in both directions, doesn't it?
Well, it's connected differently, right? I mean, if you do it, well, okay, so if you're going to do a binary state machine, I think you need 4 states. If you're allowed to do 2 tests and do a trinary state machine, then yes, I think you can reduce the number of states. I like binary state machines. Again, it's, I think very simply. Keep it simple. Now, how did you code this up in 3140? How did you code a state machine? You didn't?
More 2300, I remember seeing.
All right, how'd you code a 2300? Oh, with 2300 you build them. You didn't code them. Verilog, oh well. So in this case, a case statement is typically what you'd do. You'd have a case statement running in a task. The task is going to run every 30 milliseconds. It enters with a state, it does a test, it does a transition. We don't have quite time to write it out, I'll do it next time. But that's what you're going to have to do. Now let me, yes?
If you wrote an interrupt on a negative going transition, would that be debounced like that?
Okay, so if you do an interrupt on a negative transition, then you know that there has been a transition, and what you need to do then, probably, is to turn off interrupts for a while so that you can do what needs to be done. Then, sometime later, find out whether or not the interrupt, whether the button is still down. If it's still down, don't turn on interrupts yet. So you still have to do so. Yeah, the state of your interrupts is because you can, if you, well, on a transition, if you can interrupt on a level or a transition. If you interrupt on a level, don't do that, folks. Don't do that. If you interrupt on a level, the interrupt, as soon as you take the interrupt, it goes high again because the button's still down. If you push on it, oh, it's still down. Oh, it's still down. So you just get an infinite number of interrupts, and nothing ever happens again. So always use edge interrupts.
So just to clarify, we're not going to be interrupting on the bottom pass, we're just going to be giving the value on the transition.
For this application, and for preserving your sanity, I see no particular reason to use an interrupt-driven button system. You're clearly going to be able to do the button check inside of a millisecond. You got 16,000 cycles. The resolution I'm asking for in the lab is 1 millisecond. That's 1/200th of the time of your reflexes, and so at worst you'll have a 0.5% inaccuracy. There is no reason to use an interrupt routine here. You want to use an interrupt routine if you can't make the deadline. Let's say that you had some huge DSP thing going on. It was taking all of the CPU, and to the point where you weren't getting back to check the button, that this state machine was running too slowly. Then you would have to put the state machine in an interrupt service routine so that you could be sure that you were going to catch the event. But there's no huge computing going on here. There's no particular reason why you have to code this as an interrupt service routine or as a button interrupt. I just poll it. Just like in the first example in Sketch 1. Example, just poll the button. You'll have plenty of time. Don't make it harder than it needs to be. Inside every complicated program is a simple program screaming to get out.
Yeah, so if I understand correctly, so things like when you call, for example, the task 1, when you're doing some like execution inside task 1, the timer 0 is still running.
Sure.
And it was still like called interrupt service routine if like a compare match is found.
Yes.
Although like something may still like maybe you are still doing some like you are still executing the statement,
inside task one, right? Like things going like simultaneously. But if you do the task one, like if the task one is like
Task one better finish before the interrupt causes it to execute again. So if you have the task executing every 60 milliseconds, it better be the case that task one finishes in under 60 milliseconds, or you're going to start losing events. The interrupt service routine will happen at the correct interval, but the task won't be redispatched in time because main won't be running. Let me remind you that for this lab, you cannot fully debounce the push button. It will be incorrect if you do that, because you can't wait 30 milliseconds to find out if the button is pushed when the human is trying to time the reflexes, right? Because 30 milliseconds is actually 10 or 15% of the total time. So you have to catch the first edge, not the true edge. You do have to debounce the release of that button so that you catch the release before you are allowed to push the button again and take the system back to the start state. So you are not doing a full debouncer for this lab. You're debouncing one of the transitions, which is the release after you measure the actual time of reflexes. For lab 2, you'll have to do a full debouncer. In fact, you'll have to do a full keyboard debouncer for the whole, for 16 keys, yes.
If here we still do a like full debouncer, but we use another variable to record the first time it gets pushed.
I suppose you could do that, yeah.
That's also fine, right?
Yeah, however you do it, yeah, that's fine.
Okay.
Debouncing 16 keys is not 16 times as hard as debouncing one key. Mercifully. All you have to do is say, instead of saying is it pushed here, you replace this with you leave the first one is any button pushed, any of the 16 buttons pushed. You make this any pushed, and you make this is it the same or different? Is it the same or different? Is it the same or different? If it's different, then some button has changed state, and you have an invalid button push. If the button is the same here, then if the button state is the same for the vector of 16 buttons, then you have a valid button event. Then you wait until the vector is changed in any way. It doesn't even have to be the button led up. It could be another button pushed. But if it changes in any way, and it's the same again, then you have a release. And what will usually happen is you have one finger typing on these keypads, so it works out okay. So it's not 16 times as hard. In fact, it's hardly any more code at all to do a vector of buttons. See in 15 minutes in the lab, some of you.